Why is 2 not the right answer?
Maybe because it's cubic.
Yeah. There are 3, I have to convert 3 different meters. So it's 2 for each meter. So that's the first one, the second one, and then the third one. So it's 18.48 cubic centimeters. Or 18.48 milliliters. Okay, so I've questions here before we look at the other effect, or look at what we need to do in order to actually change the temperature. Okay. So I've changed the temperature. I went from 20 degrees Celsius to 60 degrees Celsius. And we talked about already that you need to put energy into it, so there's going to be some relationship between the energy in and the change in temperature. And of course, there's a formula. The energy in will affect the change in temperature, so there's a relationship there. But it also depends upon 2 other factors. It depends upon the mass of the object. And it depends upon something that is specific to that material. So this is a material-dependent constant. I'm going to say constant. I'll put constant in quotation marks. Yeah, it's constant as long as nothing changes. The value can change as the temperature changes, so in that sense it's not constant. Anyway, this is known as the specific heat. And for aluminum, C for aluminum is equal to 0. Let's say 0.215. Just double check that. All right, 0.215 calories per gram degrees Celsius. Or 0.215 calories per gram Kelvin. So let's sort of, before we start doing a plug and chug here, all I did was change out degrees Celsius with Kelvin here. That's the only difference between the two. But degrees Celsius and Kelvin are not the same. So how can I justify the fact that I can just replace that temperature unit and it'd still be okay?
Because it's not temperature, but changing temperature, it will be the same.
And that's it.
I was going to say, because you cancel it out by the change in temperature. If you make it the same unit, then it'll cancel.
Yeah, because the change in temperature in degrees Celsius is the same as the change in temperature in Kelvin. Because the only difference between it is some number that you add. So if you take Kelvin plus 273.15, other way around. Degrees Celsius plus 273.15, you get to Kelvin. So this is just a constant. When you do a change, 40-degree change in degrees Celsius is a 40-degree Kelvin change. All right, so we know what the mass of that aluminum block is. So we can figure out how much energy it takes. so I'm going to plug into my formula here, MC delta T. And so I've got 49.896 grams times 0.215 calories per gram degrees Celsius times 40 degrees Celsius. Or 29.
0.1056 joules.
No.
Calories.
If you look at what cancels out here, grams cancels out, degrees Celsius cancels out, we're left with calories. Oh, what'd you get?
No, I got the same.
I got the same, sir.
We got 3 people with that one.
Oh, yeah. I didn't see that 6.
Okay. Is that a lot of energy?
Yeah.
I think it's relative to what? All right.
Yeah.
Let's figure out how many joules it is. I mean, if we could somehow get this energy from, dropping an object, how much energy are we dealing with? Or if I have to lift an object. All right, so calories is a unit of energy. So I guess 2 things with this. One, how food calories. This is not a food calorie. What's the relationship between calories and food calories?
For food, it's kilocalories.
Yeah. So a food calorie abbreviated with a capital C is 1,000 calories, or 1 kilocalorie with a lowercase c. All right, so it's less than a half of a food calorie. All right, let's think about in terms of joules. Sorry. Since calories and joules are both units of energy, there's a conversion factor. And I was looking around to see if I had the conversion factor written down here, and I'm not seeing it, but I do have the specific heat of aluminum in joules per gram Kelvin and in calories per gram Kelvin. So basically 0.215 calories is equal to 0.9 joules. It's an awkward conversion, so let's figure out, so 1 calorie is equal to 0.9 over 0.215 joules. It's 4 point something.
4.860465.
Now, not all significant. So, but
1.8. I'm sorry.
okay, 4.186. And generally, these 4.186. So that's 1 calorie is that many joules. And I've got 429 calories there. So, well, let's convert. Basically, you're multiplying 429.1056 times 4.186. For the math purists, 429.1056 calories times 4.186 joules per calorie.
$1,795.
1,795.
0.378. Or that's rounded.
Okay, joules. That amount of energy to raise the temperature of that 50 gram aluminum block, so 50 gram aluminum block probably big, not yay big. To raise that temperature 40 degrees Celsius, I could lift a 1 kilogram mass, roughly 179 meters into the air. With the same amount of energy. A 60-story building, I could lift a 1 kilogram mass up the height of a 60-story building. The amount of energy it takes to raise the temperature of that aluminum. 40 degrees Fahrenheit, or Celsius. Questions to hear? And while we're on the subject of changing temperature, if I take an aluminum block and I raise its temperature, what else has to happen? So imagine, let's think of the other way. I have an aluminum block in the freezer, I take it out of the freezer and I put it right there. The block will heat up. What else would also have to happen? The block is gaining energy.
Something else would have to lose that energy?
And in this case, what would lose it?
The room and the air around it?
Yes. So there's this energy conservation still going on. If something gains energy, the other one has to lose energy. And so we got basically two situations there. We have the small object in the huge environment, like a room, and then we have the small object in a small container. Now, if it is a small object in a huge room like this, let's go sort of the other direction. So I put a hot cube in the middle of this room. It will cool off. The room will gain temperature, but that temperature is going to get spread out over the entire room, so it might not even be noticed. So if environment is large compared to object, small object will cool according to Newton's law of cooling. And when I say environment is large, basically that the change in temperature of the environment is practically zero. I put Kelvin, but if it's 0, it's also, or degrees Celsius, or Fahrenheit, degrees Fahrenheit, or Rankine. All right. Now the whole idea of the cooling is how much energy can it lose, or how much temperature can it lose, how much does it lose, and then that sets up how much it will lose from then on. So for example, if I've got the room at 20 degrees Celsius, and the block, the initial temperature of the block is 100 degrees Celsius. We had it sitting in boiling water for quite a time. We pull it out, we put it in the room. It will start to cool off. The room basically pulls energy out of it, or the block transfers energy out of it. Then, if it is 70 degrees after 5 minutes, what will be the temperature after 10 minutes? So what we have done here is establish basically what percent is going to be lost every 5 minutes. This is the Newton's law of cooling. It actually works out amazingly well. If you ever do an experiment where you've got a temperature probe in boiling water, if you take the temperature probe out, with the lab test, you take the temperature, you say, record temperature, take the temperature probe out, just let the probe sit out in the room air, then the cooling does better than that. It's a nice inverse relationship there. All right, so what we have, what is constant for a problem? Constant for a problem is the change in temperature over change in temperature actual over change in temperature max. That fraction is going to be constant for the rest of this cooling for every 5 minutes. So, first off, how much did it actually change in that 5 minutes?
Minus 30?
Yeah. So negative 30 degrees Celsius. What is the most that it could possibly lose? How cold can it get?
The same temperature as the room, 20 degrees Celsius.
So therefore, how much can it lose?
80.
Which is just 3/8. So every 5 minutes, it's going to lose 3/8 of its temperature. 3/8 of what it possibly could lose. All right, so at 70 degrees, so it's now at 70 degrees. So in the next 5 minutes, it's now at 70. After 5 minutes, what is the temperature? Well, I know that my fraction is 3/8. The most at this point it can lose is what?
50.
The most it actually will lose, that's what we're trying to find. So basically, the math problem is 3/8 is equal to x over 50. Whatever that ends up being.
18.75.
18.75? Is that what you said?
Yeah.
All right, degrees Celsius. So the temperature now, after another 5 minutes, it's going to lose that amount. So that makes this 51.25 degrees Celsius. So that's the new temperature. So every 5 minutes, it's going to lose 3/8 of what it could lose. All right, let's just do one more there. So now it's at 51.25 degrees Celsius. After another 5 minutes, what's the temperature now? Well, I know that it's going to lose 3/8 of what it possibly could lose. So what's the most that it could lose? If it's at 51.25 degrees, so the room's still at 20, how much can it lose?
31.25.
Okay. Or, I guess, for the purists out there, negative 31.25 would be the change in temperature. Delta T will end up being negative something. 1.
X equals 11.71874.
So the new temperature is, well, we were at 51.25 degrees, and it's going to lose 11.71875 degrees Celsius. So the new temperature is 49.8687. Oh, 30, sorry.
39.53125.
So if I did a